Have you ever wondered how mathematics can solve real-world problems? Well, the secret lies in the art of mathematical modeling. This is a powerful tool that goes far beyond textbooks and classrooms, transforming abstract concepts into tangible real-world applications. Imagine a bridge, if you will, where on one side you have theoretical mathematics, and on the other, you've got complex real-world scenarios. The bridge in between? That's mathematical modeling. It's through this process that we can translate situations from our everyday lives into mathematical terms, creating models that encapsulate essential characteristics and observed behaviors. These models can be as simple as basic equations or as complex as advanced computational simulations. The beauty of mathematical modeling is its universal relevance and importance. It's a tool used in diverse fields such as natural sciences, engineering, economics, and even social sciences. So, let's dive into the fascinating world of mathematical modeling. Now, you might be wondering, what exactly is mathematical modeling? Well, let's delve into this intriguing concept. At its core, mathematical modeling is a method of understanding the world around us. It's like crafting a miniature universe within the realm of numbers and equations. Imagine you're faced with a real-world problem like predicting the path of a hurricane or optimizing the routes of city buses. These situations are filled with complexities and variables, making them challenging to understand or predict. This is where mathematical modeling steps in, acting as a translator between reality and the realm of mathematics. The process begins by translating the problem into mathematical language. We identify the crucial factors, the variables that impact the outcome, and express them in mathematical terms. It's like creating a recipe where each ingredient represents a different aspect of the problem. Once we've established our mathematical recipe, we move on to constructing the model. This step involves a bit of creativity, as we weave together the variables using mathematical relationships. We might use simple equations or dive into more complex territory with computational simulations. The goal is to capture the essence of the problem in a form that we can manipulate and explore. Now, with our model in hand, we can start to solve or analyze it. This might involve calculations, working with differential equations, or running simulations. The beauty of this step is that we're no longer dealing with the messy complexities of the real world. Instead, we're in the tidy universe of mathematics where we can experiment and explore with precision. Once we've got our mathematical results, we translate them back into real-world terms. We interpret the numbers and equations, assessing what they mean for our original problem. And voila! We've gained new insights and potential solutions to our problem. Finally, we validate and refine our model, comparing its predictions with real data and tweaking it for better accuracy. In other words, mathematical modeling is the bridge between theoretical mathematics and practical problem solving. It's a tool that allows us to navigate complexity, make predictions, and discover innovative solutions in a wide range of fields. So, where do we use mathematical modeling? You may wonder. Well, it's hard to find a field where mathematical modeling doesn't make a significant impact. Let's take a look at some of the key areas. In the realm of natural sciences, mathematical modeling is like a backstage director, orchestrating the understanding of complex phenomena. Think about meteorologists predicting weather patterns. They use mathematical models to analyze data from satellites, weather stations, and radars. These models help them understand the interactions of atmospheric elements and predict what Mother Nature has in store for us. On the other hand, in engineering, mathematical models are the blueprints for innovation. Consider how civil engineers optimize urban traffic. They use mathematical models to simulate traffic flow, identify bottlenecks, and design smarter traffic management systems. By doing so, they aim to reduce congestion and make our daily commutes smoother. Next up is economics. Mathematical models here are like crystal balls, offering insights into future trends. Economists use them to forecast economic indicators like inflation, unemployment rates, and GDP growth. These models help policymakers make informed decisions, aiming to ensure economic stability and prosperity. Last but not least, mathematical modeling also plays a significant role in social sciences. For instance, in sociology, it's used to understand population dynamics. Sociologists develop mathematical models to study patterns of migration, birth and death rates, and social interactions. These models provide insights into how societies evolve and help in planning for future societal needs. So, from predicting a thunderstorm, designing a traffic light system, forecasting economic trends, to understanding societal changes, mathematical modeling is everywhere. It's like a universal language, bridging the gap between abstract mathematical concepts and tangible real-world phenomena. As you can see, the reach of mathematical modeling is extensive, impacting various aspects of our lives. Whether it's making our commutes easier, helping us prepare for weather changes, guiding economic policies, or shaping societal understanding, mathematical modeling continues to be a powerful tool, transforming abstract math into practical solutions. How do we go about creating a mathematical model? You might be wondering. Well, the process of mathematical modeling is like a journey that navigates through several essential stages, each with its unique purpose and significance. Our first stop is problem formulation. It's where we identify and define the real-world problem we intend to tackle. This step is like setting the coordinates for our journey. We need to understand what we're dealing with, the variables involved, and the questions we're trying to answer. It's about turning a foggy landscape into a clear roadmap. Next, we arrive at model construction. Here, we get our hands dirty and start building our mathematical model. This model is a simplified representation of the real world, capturing the relationships and essential variables related to our problem. It's like sculpting a statue, where the raw clay is our understanding of the situation, and our tools are mathematical expressions and equations. Once our model is constructed, we venture into the realm of mathematical solution. This stage involves applying mathematical methods to solve or analyze the model. It might involve calculations, differential equations, or even complex simulations. It's like deciphering a coded message where the code is our mathematical model, and the message is the solution to our problem. Then we move to interpretation of results. This stage is about making sense of the mathematical solutions we've obtained. We interpret these results in the context of the original problem, assessing the relevance and accuracy of our model. It's like translating an ancient script into a language we can understand, with the script being our mathematical solution, and the translation being its real-world interpretation. Finally, we reach validation and refinement. This is where we compare our model's predictions with real data to validate its accuracy. If necessary, we refine our model to improve its precision. It's like testing a prototype car, where the prototype is our model, and the test drive is the comparison with real data. If the car doesn't perform as expected, we go back to the drawing board, tweaking and refining until it's ready for the road. This process, while rigorous, ensures that we create accurate and effective models to solve real-world problems. It's a journey of exploration, creation, and discovery, where the abstract becomes tangible and the theoretical transforms into the practical. It's the art of mathematical modeling, an essential tool in our quest for understanding and solving the mysteries of the world around us. Mathematical modeling isn't just for professionals. It also plays a crucial role in education. Let's delve into how this tool shapes the minds of young learners. When we think of mathematics, we often picture a labyrinth of numbers and equations. Mathematical modeling, however, transforms this abstract maze into a tangible landscape. It challenges students to apply their knowledge in practical settings, pushing them beyond rote memorization and towards critical thinking. Imagine a student tasked with modeling a city's traffic system. They must consider factors like peak travel times, road layouts, and vehicle speeds. This isn't just a number-crunching exercise. It requires problem-solving, creativity, and a deep understanding of the mathematical principles at work. It's no longer just about getting the right answer, but about understanding why that answer makes sense in the real world. By encouraging this kind of active engagement, mathematical modeling fosters a deeper comprehension of mathematical concepts. It moves students away from the mindset of mathematics as a series of disconnected topics and towards seeing it as an interconnected web of ideas with real-world applications. Furthermore, mathematical modeling highlights the relevance of mathematics. It shows students that the equations they grapple with aren't merely academic exercises. They're tools for understanding and addressing real-world challenges, from climate change to healthcare. In essence, it transforms mathematics from an abstract discipline into a dynamic toolkit for problem-solving. In conclusion, mathematical modeling is more than just a method for translating the real world into mathematical terms. It's a bridge between abstract theories and concrete realities, a tool that breathes life into mathematics and makes it accessible and applicable to everyone. So, whether you're a student or a professional, Mathematical modeling is a powerful tool that brings the abstract world of mathematics into the concrete realm of real-world problem solving.